generation of quantum technologies accessible. And today we will talk about Delta Kit making quantum error correction accessible. Welcome.
So thanks for the introduction. One quick correction, I'm not working as an entrepreneur anymore, full-time at Riverlane. So, more to be said. So my goal today is to present you a toolkit that was made open source by Riverlane a few weeks or a few months ago on quantum error correction. But first, okay. So my way of attacking the presentation will be through running quantum error correction experiments on real hardware and the difficulties it brings on the table. So just a quick example, Google, one company you might know about that is doing things in quantum computing. They started their quantum computing team in 2014. They had one scientific paper in 2013 about quantum algorithms, but not about quantum hardware. So let's say they started in 2014. 5 years later, they announced their first public chip, which was called Sycamore, and they have made no claim about quantum error correction at that time. They just made a claim about quantum supremacy that people ended up disproving because they were able to simulate the experiment more efficiently, if I remember correctly. So small hiccups on that. 10 years after starting, they finally unveiled a new chip, Willow, where they announced for the first time a good result in quantum error correction, which is we are actually able to correct errors from the hardware. So it takes a company like Google with a few hundreds of scientists and top scientists and a lot of money, 10 years to achieve that. This is just to show you this is not easy feat. It is a hard problem. So during this talk, what I will do is first give you a very special introduction about quantum error correction, where I won't go at all into the theory. And I will just give you some rules about how it works. These rules will be from the theory, derived from the theory, but you don't need the theory to understand the rules. These rules should be enough to understand the end or the rest of the talk. Then I will start introducing some complications due to the hardware and show you how you can see them, how you can try to fix them, and why you need to do that to eventually have something that runs on the quantum computer, because that's our goal here. Fine? Yeah, go ahead.
Because you mentioned the surface code here, the rules you will state will apply for any stabilizer code.
No. Yeah.
Okay.
Yeah. This is just, so my goal here is just to make an example. Because most of the results on hardware I will talk about were done with surface code. I think that's the best example. So the rules I'm about to tell you are not generalizable in general. Some of them are, not all of them. And I will mention it. I will mention it. And then once you will see that whole stack of complexity, I will show you how Riverlane is helping you, reducing the complexity by implementing things and giving them to the community. One point, if you have any question during the talk, ask them, raise your hand on Team. I hope I will be able to see you. If not, just unmute yourself and start speaking. Cut me right in the middle. I'm fine with it. The goal is for you to understand what I'm saying. If I'm not able to finish my slides, that's not the main problem. I would prefer you to come out from here with additional knowledge rather than with a full set of slides you've seen. So with that, let's start. This here is the surface code. It is a visual representation of a quantum error correction protocol, which is called the surface code. This whole picture can be seen in different ways. This is an exact representation of a large quantum circuit. You don't see it, but it is. This is also a representation of several small squares and triangles of different colors that each of them are a representation of a smaller quantum circuit. So the whole picture is basically small quantum circuits that are glued together. The colors here are important, and you will see why after. The dots here are physical qubits. The colors of them are just because the green ones are called data qubits, and the orange ones are called ancilla qubits or syndrome qubits. You can see like green ones are the support of your logical information, whereas orange ones are here to help with the quantum error correction. Now, a few rules. Again, these rules work for the surface code. They are derived from the theory, but they are not generalizable for every code. First, if you have an error on one qubit, the shapes that touches that error will light up and detect the error only if they are opposite color of the error. So here, error is green. It touches 4 shapes. 2 of them are green. Don't know if it's green or blue on the screen, but let's say it is green. 2 of them are green. They don't light up because they are the same color as the error. The other 2 are gray. They light up. This lighting up process is what you will see on the hardware. When you run your quantum computing experiment, you will see 2 measurements lighting up, saying there is an error nearby. 2 more rules. Detectors, so these things lighting up, only fire, so they only light up when they touch an odd number of errors. So here you have 2 green errors. This one, maybe I should point with the mouse so that online people can see easier. This one here is touched by 2 errors, and so it does not light up.
Right there.
Sorry?
So you can use the pen right there, so you can point out.
Oh, I can point out with that?
Yeah, but
Oh, it's fine with the mouse. Yeah. So this one does not light up because 2 errors of the opposite color are touching it, whereas this one and this one light up because only 1 error of opposite color is touching it. You can add more errors because most of the time your hardware is noisy. And it turns out that when you do a chain of errors, only 2 detectors will light up. This is only valid for what we call matchable codes, surface code being one of them. The color code is not a matchable code. So this property that a chain of error only light up 2 detectors is valid, but not for every code. And in fact, this is one of the reasons why we use the surface code, not the only one, but one of them. It is because such constraints, such a property makes the decoding work easy. What is, oh yeah, one more rule before speaking about decoding. If you do the rules here, you will see that boundaries tend to absorb detections. So here, if you look at all the gray shapes, they all have 2 errors touching them. And so on when you touch a boundary, only 1 detector will light up. And so now you have a decoding problem. This is what we call a decoding problem, which is your hardware is giving you that measurement result, saying, I've seen something here. Your job, or the job of the decoder, is to find back the most likely source of errors that result in that syndrome, in this syndrome. So here, it's easy, because we've seen just before what were the errors. But now let's say I'm giving you that syndrome. What is the most likely chain of errors that result in such a syndrome? This question is interesting. This question is what the decoder is trying to answer. So there has been a tentative answer in the audience saying on the left. It does not work because if you look, for example, error here, error here, error here, this one here will light up. Boundaries are not the same. Two boundaries are gray, two boundaries are blue. And so the colors of errors depends. So yes, the answer is, the answer could be this one, but the most likely answer is rather, I thought I had it, this one. Here, these 4, because often getting 4 physical errors is more likely than getting 5. So that gives us more properties. You can correct an error if the error is less than d-1/2 physical errors, d being the distance of the code and being basically the number of qubits in a line. So here it's 9. As soon as you have more errors than that, you can correct, but you will likely correct it wrong. For example, if that is the error that actually happened, so 5 physical errors, my decoder will very likely tell me this is the error that happened. This is an incorrect correction. And so you fail to correct correctly. And so you have an error, a logical error. So this is basically the limits of error correction. You can tolerate a given amount of errors up to a point. And when you have too much errors, you start making mistakes. If you continue that chain here of errors, you can see that at least one detector will light up until you have a line of D errors, bridging basically one boundary to the other. That means that as long as your errors are composed of less than d-1 physical errors, you should be able to see it. You see something went wrong. You don't know if you will be able to correct it or not, because maybe it was a d-1 chain of errors, or maybe it was one error. If it is one error, you can correct it. If it is d-1, you will correct it, but you will make a mistake when correcting. Again, I encourage you to ask any question if you have any. Now, you might have seen these kind of plots, very detailed plots. These are very important in quantum error correction because they allow you to check that what you implemented works in practice. The x-axis here is the physical error rate. It is basically the probability for one physical error to happen at any time. It is a little bit more complex than that, but going with that is fine. On the y-axis, you have the logical error rate. This is basically the probability for your decoder to answer incorrectly. As we've seen before, the probability that your decoder answers incorrectly is this one. So the probability that a d+1/2 long error happens. And this is what we have here on that plot. So logical error rate in y-axis, physical error rate in x-axis. These lines that you see here going down are the logical error rates for a surface code with respect to the physical error rate for different distances. So here, the blue line is a distance 3 surface code subject to an increasing or decreasing, depending on which side you go, amount of physical noise, and it gives you a logical error rate. This line, the orange one is a distance 5, and this line, the green one, is a distance 7. So let's take one point, for example, this one here, and explain what it means. This point is a distance 5 surface code because it's on the orange line. It has been implemented, so you have quantum circuits. You add noise that is 10 to the power of -3. So the probability that an error happened at any time is 10 to the power -3. And it gives you a logical error rate that is approximately 3 times 10 to the power -3. So not as good as the physical error rate, but the main promise, the main claim of quantum error correction is that if you lower the noise, there is a point where it becomes more interesting. And if you increase the distance at a low enough noise level, physical noise level, your logical error rate will decrease exponentially, will be close to 0 exponentially fast. This point where it starts being interesting is called the threshold. And this is what you see here. So this is an inset plot of that part here. And what you see here is that there is a crossing point where distance d equals 7, so in green code, becomes more efficient with lower logical error rate than distance equals 5 or distance equals 3. And before that point, so with higher error rate, this is the opposite. This is basically the point where your code starts correcting errors efficiently, in a sense. One last thing about that, there is a very important number that is called lambda, which is a capital lambda here. That is basically a multiplicative factor, and it gives you how much you reduce your logical error rate by increasing the distance by 2. The Google experiment in 2024, so a year ago, with the Willow chip is basically the first one being able to say we measured a lambda over 1 of 2.14. 14. What that means is that their chip is able to correct more and more errors when they scale up the distance. But this is a theory. There is a lot of things happening in practice. It is also good time for questions. If you have any questions on what I just talked about, good moment. Yes?
One really quick one. So the surface codes that I've seen today and yesterday were always basically torus codes, right? There's 4 squares at each. There's 4 stabilizers to each data qubit. I believe to have seen that that you can do surface codes where you have more than 4 squares or more than 4 ancillaries to each data qubit. Does it make a difference? Is this even interesting?
I'm not even sure. So there are details of implementation of the surface code where you might have to use more data qubits. For example, I have something that spans 2 of these here, but I'm not aware of a practical implementation where you try to measure stabilizers, because these are basically measuring stabilizers that are on more than 4 qubits. I may just not be aware of it.
Yeah. We can talk after.
Yeah, okay. Any other question? Again, the goal is for you to understand everything. So no stupid question, ask. Just ask, and I'll try to answer, try my best to answer.
How is the lambda connected. You said, I mean, I understand threshold, like when the distance is more than 7, then. But how is the lambda connected to it again? I didn't understand.
So lambda is basically the amount by which you reduce your logical error rate when you increase or decrease the distance by 2. This is a definition of lambda. When you are below threshold, so on the right part, on the left part here, lambda is over 1, which means that when you increase the distance, you reduce your error rate. When you are on the right portion, so below threshold, lambda is below 1, which means that when you increase your distance, you're actually doing more mistakes. And this is due to the fact that this is a protocol we use to correct errors. You do gates with this protocol, and the more you scale, the more opportunity for physical errors you have, because you're using more qubits, you're doing more gates, etc., etc. And so the threshold you have here is basically sweet spot between the amount of physical errors you do and the strength of the error correction.
A perfect balance between the entire number of qubits we are using. Like the more physical qubits we use, just like you said, the more physical qubits we use. So there has to be a perfect balance between that, right? Like
yes. Oh, so it's not really a balance, because as soon as you are below threshold, the more qubits you had, the larger the code you can do, and so the lower your logical error rates can be, by definition of what the threshold is. So below threshold, you want to have more qubits so that you can scale up your code and have lower error rates, logical error rates. Above threshold, you don't want it. So what can happen? These quantum error correction codes were devised to handle colored errors, like I've showed you before. And by colored, I mean poly errors, for those that are a little bit aware of the theory. These are only one type of error, not all of them. For example, on some superconducting devices, you might have leakage, which is your qubit not being in the 0 or 1 state, but being in the 2, 3, or even 4 state, which are non-computational states. This happens, and you don't want this to happen. And the problem is that quantum error correction codes are not made to correct these kind of errors. For example, with atoms, a company like Pascal, this is from a paper from Pascal, they have a lot of atoms, but sometimes one of them is lost, just disappear. You lost it, you didn't trap it well enough, and it disappeared. This is another type of error that is not a poly error, and you need to be able to handle it eventually if you want your quantum error correction experiment to make sense. Because if you just lose one atom and the whole computation is over, probably you will not be able to do a lot of things. Something else, correlated errors. So turns out that if you don't protect your chip well enough, you will have like high energy particles striking your chip and doing a large correlated error. This is from one of Google paper, where you can see everything is going fine, high energy event going there with a lot of errors, and then it slowly goes back to everything is going fine. The problem is that when you enter that regime, it is very likely that your whole computation will be over if you don't protect against that. Also, again, quantum error correction codes are not made to protect that. One of the fundamental assumptions of the efficiency of quantum error correction codes is that errors are uncorrelated.
I have one quick question. So the system then become normal after So it means when we make a measurement in this case, is a system can we able to get a good results when a system become normal?
So yes, if you're doing a computation here,
Yes.
system becomes very noisy. You just have a lot of errors, and very likely your computation will have errors in it. You can continue your computation if you want, but there is a high chance that your logical computation is faulty just because you had a lot of errors. The worst that can happen for surface code is a correlated error in line. If you have like one error that gives you one line of qubits with an error, you're done. Like the surface code is not able to protect against that, or at least the classical version, the standard version of the surface code is not able to protect against that. And the numbers I give you here are assuming that errors are not correlated. So there is an equal chance that, or approximately equal chance that an error will happen here, 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 or here. And that if an error happens here, there is not a higher probability that another error will happen here, for example. And in practice, this is never checked. But this is also fine in the sense that these correlations are small or small enough for us to be able to show things.
Yeah. Is there any theoretical or any work who try to fix the correct errors or?
Yes. Yep. So I'm about to show about leakage, but you have things for each of them. So I will speak about leakage, so I won't go into details here. Atom loss, I'm not an expert, so I don't really know how they handle it. I know there is something to handle it. I'm not able to explain it yet. For these, it's basically improving the hardware. Improving the hardware so that when a high energy event appears, the hardware is more resilient and experience less errors. And I think they do that by trying to decouple the frequency of qubits and trying to make neighboring qubits with a large difference in their driving frequencies. I'm not a hardware guy. I might just say something wrong here. So check again, just in case.
I'm sorry, are you hardware agnostic or is it like you?
By you mean Riverlane?
Yeah.
Trying to be.
I mean,
In fact, so my personal opinion is that trying to be hardware agnostic is a dead end, because you need to know about all of these in order to make quantum error correction work. This, as far as I know, only happens on superconducting qubits. This only happens on atom-based modalities. This may happen on others, but may not happen on some qubit modalities. And in general, different ways of making qubits have different trade-offs. For example, here, with atom-based solutions, you are able to move atoms. And so you are able to interact, for example, this qubit with this qubit by moving them, which is not possible on superconducting devices, for example.
made more sense as a company to maybe focus on specific platforms.
Yeah. So you need to tailor your quantum error correction code to your hardware. Else, you'll just leave some performance on the table, and in the end, you cannot afford it because it's a hard enough problem.
Yeah. Then in that case, do you have any preferred platforms that you're showing to me?
Again, not about Riverlane here. Personally, I've always been taught about superconducting qubits, and so this is a platform I know the most. I understand the trade-offs. I kind of understand the high level of how they work, which is absolutely not the case for atom-based or other modalities. I would need to be better at that, but also there is so much stuff going on that I'm only a human. I have 24 hours in a day, and that's it. And I need to sleep. So, one example for leakage. This is a different color. This is blue, just to tell you it's leakage. It's not a polymer of green or gray color. The problem with leakage is that it can appear at any time, like any error in the hardware. And then it spreads, and it spreads again. And this gives problems because you cannot, or at least it is hard to see it, detect it, and correct it quickly enough so that it does not spread everywhere. There are, nevertheless, potential solutions. For example, you might be able to calibrate your hardware to know about its leakage properties and give that information to your decoder. We do have at Riverlane decoders that are doing leakage-aware decoding, where the decoders knows about the leakage properties in the hardware and tries to solve the problem knowing that leakage can happen, and knowing that it is yet another error we try to solve. You can also try to do mitigation. And I think this is what Google is doing at the moment. Basically, they do that by implementing a specific kind of measurement or reset, can't remember, that has the property that it will take leakage to a leaked state, for example, 2 or 3, to a non-leaked state. And it will basically transform a leaked state into a poly error, which is something we can correct with surface code. And then you have other techniques I won't go very deep into, but one way of implementing that surface code in practice is to make it wiggle by moving it 1 qubit across and moving it back. So what you can do is move that patch 1 qubit across and move it back. And this is interesting because the orange qubits are measured at every round, whereas the green qubits, your data qubits, are not. And measure is able to remove leakage. And so what you do is you measure each qubit at each off round, or at every 2 rounds, each qubit is measured. And by doing that, you stop leakage from spreading. Yes.
Such a measurement can definitely remove leakage. Isn't there a risk that it also destroys some of the information of the logical state? Because it's then the loss is in a Pauli error. Then you fix that.
So this is a good question because you end up measuring all the qubits, but your logical information is moving at each round. So the green qubits will move. You will always measure orange qubits, in a sense. Basically, you move your information. You move the whole patch 1 step, you measure, then you move it again. So basically, you can see that as your qubit grid and your patch applied on that qubit grid. Are people just, yeah. So your qubit grid and your patch applied to your qubit grid, you're moving your qubit grid a little bit so that each physical qubit is measured every 2 rounds.
Okay.
That is like a mitigation strategy. It does not remove leakage, but you can mitigate for it. And as far as I'm aware, Google went leakage mitigation at the moment. And for their Willow paper, they did leakage mitigation. So this is one problem. How can you see it? This is from the Willow paper from Google, and I will explain you what it means. But this is a way of seeing it. If you remember correctly, here, each of these shapes here, triangles and squares, are detectors, and so they will generate data at each round of error correction. So what you do in quantum error correction is you take that quantum circuit and you apply it again and again and again and again, trying to find errors and trying to save your quantum operation, trying to keep your quantum information intact in time. And each of these here will generate measurements, a lot of measurements. What you can track is whether or not they detect quantum errors on time, with respect to time. So here, for these 4 plots, you have time going from left to right. Increasing time is going from left to right. And what you see here is the frequency at which each square and triangle is outputting there is an error somewhere. So to rephrase a little bit, using, for example, this plot, what you see for one line of this plot is one of the square, and this line is telling you, oh, approximately this square raised an error 10% of the time. So 10% of the time, this square said there is an error nearby. Here I'm signaling you this error. And what they showed, so this is again from the Google paper, is that without leakage mitigation, you have that detection rate that goes up because leakage is spreading. And so more and more detectors are experiencing leakage. And because you cannot correct it, or it is hard to correct, your detection rate is going up. Whereas here, when you do leakage mitigation, and again, I think they do that with a specific measurement, the rate at which detectors are firing up stays constant, except first and last round, but these are outliers, expected outliers. So this is a way to see from your quantum hardware results that you have leakage. It is not the best way. We don't know for sure if that is due to leakage, but Google people said it is probably that. When we try to mitigate leakage, it disappears. Maybe that's enough to say it is caused by leakage. So that's a way of seeing that your quantum hardware is experiencing something like leakage, and a way to see that you need to mitigate for leakage in order to have better performance. Another way is to try to do error budgeting. So you do that. I won't go into the details of how you do that. Basically what you do is you compute your lambda. You take 1 over that quantity, and there is an assumption that says that each error mechanism, different error mechanism, should be approximately linear in, so 1 over lambda should be approximately linear in each error mechanism. With that assumption, what you can say is, I have 1 over lambda. I would like 1 over lambda to go to 0, because if 1 over lambda goes to 0, that means that lambda goes to infinity, and that means that whenever I'm increasing the size of my code, error correction code, I will gain a lot of logical error rate. And you can decompose 1 over lambda that you want to go to 0 eventually. You can decompose it as different contributions from different error mechanisms. Here, CZ being the 2-qubit gate, stray interaction being crosstalk when you do CZ, when you do 2-qubit gates, idle being when qubit is doing nothing, measurement, leakage, 1-qubit error, and that is basically something that we miss in the method. This is the amount of information we're not able to reconstruct, and we hope that this grayed out area here is small enough for us to get some useful results. So what that tells you is that if you try to reduce idling errors on your hardware, it will have a low impact on your 1 over lambda. And so it should not improve by a lot your efficiency, your error correction efficiency. You want to target large things here, because if you reduce, for example, CZ by a half, that means you will reduce 1 over lambda. So if you reduce CZ here by a half, that means you will reduce 1 over lambda by this whole quantity here, and that means your lambda will increase a lot. So this is basically a tool that allows hardware people to know what to prioritize, to see, oh, my CZ error rate contributes a lot to my error budget. I should target that first, because if I don't target that, I will never be able to get some very interesting numbers. And so everything that I showed you, every plot that I showed you here, can be made with DeltaKit. So this was my very long introduction. I still have 20 minutes to go. Again, that's a good time for questions. The next section will be showing you DeltaKit in practice, the library, software library we at Riverlane are building for quantum error correction, and how you can set up a very basic quantum error correction experiment with DeltaKit. If you have any question, that's a good time. Okay, no question. So let's go. So very large overview of what DeltaKit is doing. We do have circuit generation. So basically, let's say you want to do error correction with the surface code. In the end, you need to generate the quantum circuits. You need to generate the gates, native gates that your hardware will implement, will run in order for your quantum error correction code to be able to work. This is what I call circuit generation. So in DeltaKit at the moment, and we are actively working on improving that, we have circuit generation capabilities for repetition code, rotated surface code, unrotated surface code, and the BB code, the IBM bivariate bicycle code. Then you want to be able to manipulate and change a little bit your quantum circuit, because you generated something, but maybe your native gate set on your hardware is different than the one we use for generation. So you want probably to be able to compile efficiently to your native gate. You may also want to be able to schedule gates differently, depending on your hardware, depending on the time it takes for a measurement or a 2-qubit gate on your hardware to execute. Maybe your hardware is able to do 1-qubit gates on some qubits and 2-qubit gates at the same time. Maybe not. Maybe you want all your measurements to be scheduled at the same time. Maybe not. Depends on the hardware again. And that's where like the hardware agnostic approach breaks, because you want to run things on the hardware. So you need to adapt to the hardware capabilities. Also, if you want to go simulation, we have plenty of noise models that try to mimic what the hardware is experiencing in terms of noise that you can add to your quantum circuit in order then to simulate them and to not have to run on real hardware. Then we have simulation capabilities. So you can also do that with a QPU if you have access to one. Very few people have access to one. So often we do simulation. Once you've done your simulation, you have all your detection events. So again, the shapes that light up, this is the output of your quantum hardware. And you want to decode that. So you want to try to find where the physical hardware errors happened so that you can correct them. This is done with the decoder. And this is actually the main thing Riverlane is doing. Implementing very efficient decoders for quantum error correction codes. One thing I didn't talk about, and I think I don't have it in the slides, you want your decoder to be efficient in the sense it gives you correct results, but you want it to be efficient also in the sense it is very quick, and also in the sense it has a very low latency. And by very low, I mean, so by very quick, I mean this doing one round and generating measurements for superconducting qubits, this is 1 microsecond, approximately. So this is quite quick. You need to be able to process the information in less time. If you don't, then you will have a backlog of information you need to process, and you will end up with large amount of data, which is not something you want. And you also want low latency, because in the end, the latency of your decoder will dictate the logical clock rate of your quantum processor. This is the latency of the decoder. This is not how quick the gates are. This is not how many rounds you can do per microsecond or per second. This is the latency of the decoder. And so you want the latency of the decoder to be very low. In order to be very low in terms of latency, we at Riverlane are implementing decoders using FPGAs, which are basically reconfigurable hardware that is way more efficient than running on a consumer CPU or GPU and running like software on a consumer CPU and or GPU. And then, so once you've tackled that decoding problem, which is very hard by itself, you have a whole lot of result analysis things. Most of them I've showed them before. This one is the detector error rate, the detector probability, and this one is error budgeting. Do you have any questions? I still have 15 minutes to go. The remaining slides are basically code to show you how you can use DeltaKit in practice. If you have questions, right moment, as always. Yes.
I have one maybe on this last comment that you use this reconfigurable hardware. So am I kind of reading this correctly in that, I mean, the decoder is running on a classical computing device?
Yes.
But perhaps the hardware of such a computing device also has yet to be built in a certain sense. You don't want to use the typical stuff that's been used these days. You need something specific.
What do you mean by typical stuff? You mean software implemented on consumer grade CPUs?
I think that's in here, for example.
Yeah,
like
you don't want
to.
So if you use one of the decoder based on sparse boson, it is the problem it solves is called minimum weight perfect matching. So I'm speaking about this one here, minimum weight perfect matching. This one, so it is able to meet the requirement that it processes data fast enough so that you don't have a backlog on good CPUs. But you don't have the latency. The latency is high. And the problem with that will come when you will start doing T-gates, non-Clifford gates, or T-gates. And when you will have to wait for the output of your decoder to do something or something else, depending on the output. When you wait for that, you need to make your hardware wait. And the longer it waits, the longer your computation is. By hardware, I mean quantum hardware. So that is why latency is also very important. And here, low latency means like a few microseconds, a few dozens of microseconds. So I don't know what the latency of regular computer would be when connected to a quantum hardware. But if you don't have a tight coupling, tight integration of the decoder with the hardware, you will likely not be able to meet these latency requirements. Just transmission of information, not even computing, but transmission of information can be a bottleneck because you need to do transmission of a lot of data in and back of one data. But the amount of data you transmit is not really a latency concern in a sense. It is kind of, but simplifying things. Yes.
With DeltaKit, is it possible to simulate more complex fault-tolerant protocols?
Yes.
Like lazy surgery.
Yes. So in practice, this will very soon probably be improved. At the moment, in terms of simulation, we are using STEAM. So everything STEAM is able to simulate, DeltaKit is able to simulate. Which means anything that is only composed of Clifford gates should be simulated. And so if you have a lattice surgery experiment with Clifford gates, Steam can handle it. So DeltaKit will just give it to Steam. Okay, few examples of code, because we're here for code, or I'm here to show you code at least. So how you can generate the quantum circuits, implementing your specific error correction protocol. With DeltaKit, that's pretty simple. You just have to instantiate something that represents your code, and then you call a function. And that should be enough to give you a quantum circuit implementing the code by itself. So here on the left, you have rotated planar code, which is the surface code I showed you before. This is exactly the same thing, different name, but the same thing. And on the right, you have the repetition code, which is often used for tutorials because it is simpler to understand and it is easier to plot as a quantum circuit that makes sense, whereas this is just a mess for humans. This is hard to understand for humans. Then you can compile it. So by compiling, I mean changing the gates that are used to measure your stabilizers and to detect errors so that the gates that are used in the end are the native gates that are implemented in your hardware or IBM hardware, Google hardware, Pascal hardware, C12 hardware. Yes.
So where we can select the backend in there.
By backend, you mean simulation backend?
Yeah.
After.
Yeah.
So this is just about circuit generation. This is basically the first box here. After that, so circuit generation, after that, you manipulate your quantum circuit, you change it a little bit, then you simulate it, then you correct it, and then you analyze the results. This is very much like an iterative process. And ideally, once you have analyzed your results, you come back at the circuit generation step, try to improve that, try to improve your hardware, and you start again. And you improve, continuously improve, up to the point where you have an error-corrected quantum computer that is able to simulate chemistry experiments. So that's how I see it. Yeah, go ahead.
It will take a very long time to take a whole look. So it depends on the problem, right?
So it takes a very long time to improve your hardware. Because when I say just improve your hardware, this under the hood is a lot of people doing research about how you can implement that more efficiently, then a lot of people building the research into real chip, then a lot of people calibrating the chip, then a lot of people running things on the chip. And so it takes a lot of time. That is why sometimes you prefer to do simulation. Simulation is not exact. It will never give you exactly what the hardware is giving you. But sometimes it is close enough and you don't have to do like this whole process that costs time, but also costs money. People researching stuff, people building quantum chips, people integrating quantum chips into a software stack and everything. And so simulation is like a first step to try to do. And if you have a good noise model, you might be able to simulate something that looks like the behavior of your hardware.
If I understand well, the QEC is run on the classical computer, right?
Could you repeat your question?
I mean, we correct the error.
Yep. So
by using the classical computer.
Yes, this box is fully classical.
Okay, so we'll be able to speed up the full loop using for example, GPU or something like this.
Try it. So NVIDIA is trying it. A lot of people are trying to tackle that decoding problem. It is a hard problem. And we at Riverlane are tackling that hard problem by building specialized hardware for it. Because software is slow in that specific instance where you need very fast response rates, you need very low latency, and you still need to be able to process a large amount of data in less than a microsecond. So it is a hard problem. You can try to improve things. A lot of very intelligent people tried already.
It's compatible with like just superconducting hardware or like every sort of?
It should not. It should be compatible with any kind of hardware. It is very much up to the hardware provider to see if the quantum circuits that are output here can be ingested by their QPU. If it cannot, then maybe we can do things in DeltaKit to help with that. Maybe it's up to the hardware provider to do that. What DeltaKit is outputting is a physical quantum circuit with physical gates. So the hardware provider, the QPU, will still have to do a lot of work to translate these gates into pulses or into, I don't know how you control atoms, but in superconducting, you do pulses, microwave pulses. This translation is done by the hardware provider because who else can do it?
Like, have you experimented with all sorts of hardwares? Like, because you're talking about simulation, so like, have you actually tried with like real? You have, I'm guessing.
So we do have several partnerships with hardware companies. Yes.
So like, you have tried with different sorts of hardwares, and you have gotten like good results and.
Depends what you ask. What you
Photonics, trap times and superconducting. Is it work one with the better with one kind of and one like less?
I don't know. I would not be able to tell you exactly all the hardware companies we are partnering with. That's not really my stuffs anyway. And I don't know. And probably even if I knew, I wouldn't be able to tell you that. But I don't know, so I'm not able to tell you that. And I think that's approximately time. So I'll just shotgun the slides on code. And so building a quantum circuit, compiling that quantum circuit to a native gate set, compiling a quantum circuit to a native gate set plus adding noise. And you might define your own noise models. Then once you have a quantum circuit, you can simulate it with STIM. That gives you measurements that you can translate into detectors and observables. And then you can decode it using either open source decoders that are in DeltaKit or closed source but openly accessible decoders implemented at Riverlane and accessible through a cloud API. And once you have decoded your results, you can do a whole lot of analysis on your results so that you know what went wrong and you can try to improve your code, your decoder, your hardware, or anything that fails. Thanks for listening. I hope you come with more, you get back with more knowledge than what you get in. And thanks, thanks a lot.
Have a last question, or is already?
I think it's time for the next.
It's fine.
It's fine? Go ahead.
Yeah, I have a next question. What if I have a brand new error correction code? I know what are the stabilizers, but I would like to find an efficient syndrome extraction circuit. So does DeltaKit help with that?
At the moment, it might. We internally, we do, it's a question online. Yeah. Okay, at the moment, we do have a few things internally in DeltaKit that do that. I'm not sure whether or not it is generic enough to do that because that's a part of DeltaKit I was not involved a lot with. And so we do have things. it is probably able to do that, but I'm not 100% certain, 100% sure, but probably. Yes, I see a raised hand. Go ahead. We don't hear you. You have your mic shut off. Don't know
Hello.
that. Yeah.
I hope you can hear me now.
Yep, I can.
Yes.
It's a little bit low, but I can.
Amazing talk, by the way. I just have a question on quantum error correction. In your perspective, or in Riverline's perspective, what is the biggest bottleneck right now facing quantum error correction and that scientists are working on to be able to fix? And my second question is, does Riverlane have opportunities for collaboration for master's dissertation thesis?
So first question, I think the question is ill-posed. You should say, what are the different bottlenecks for quantum error correction? The first one is better hardware, but then that's not all of it. Sometimes you can just, through clever implementation, reduce the requirements on the hardware. So hardware, software, and theory are the main bottlenecks, and are basically what all of us as a community should work on, finding better codes, then finding better implementation of those codes, and then implementing them on better hardware. We should improve on all of that. So yeah, I would say that. Second question, if you go on riverlane.com, you have job openings. I'm not sure if some of them are for master student levels. Check it. If you want, I will send my email address in the Teams chat. You will be able to send me a mail and I will give you a better answer.
He is in Discord too.
Sorry?
You are in Discord too, the Discord channel.
Yes, I'm in Discord under the handle Nelime, Nelimee.
You can see on guests and speakers channel, and he's there. Any more questions? So thank you a lot. Thank you, Adrian. Thank you. So for the networking, I think it will be on site. We would like to say see you again on the afternoon section for the online participants. See you later. See you in 1 hour, like 2 hours. Yeah, 2 hours. See you.
should be unmuted. Maybe could someone online can tell us if that works?
Light.
Good afternoon. Am I audible?
Yeah, well, good. Well, good.
We have Leonardo too.
Yep, it works.
Nice.
Welcome everyone. I am Poonam Kumari on behalf of the entire organizing team of Qiskit Paris-Saclay edition. I welcome you all to our panel discussion. We have had extraordinary talks in the morning, and now we have the chance to bring together experts from both hardware and software industries for our panel discussion. Before we dive into the discussion, I'd love for each of our panelists to briefly introduce themselves. Please share a little bit about your background, your current role, and the type of work you focus on. Let me start with Jesus first from C12, please.
Oh, okay. So my name is Jesus. I'm originally from Spain, and right now I'm working for C12 Quantum Electronics. So we're a company based in the 5th arrondissement of Paris, and we are hardware providers, quantum hardware providers, although we also have an emulator right now, which is part of our value proposition. I joined C12 1.5 months ago, but I really like what I do. I joined the business development team. Although I have to say I have a background in nanofabrication and also nanoscience, but not right now. Yeah, I'm doing business development, so talking to clients and partners to, to launch the different projects and proof of concepts. So nice to meet you.
Hi everyone, I'm Miriam. I work for Unitary Foundation, which is a nonprofit organization that's focused on open source software and quantum. I myself don't have a technical background. I think I'm one of the rare ones, but I'm coming from investment banking and switched to quantum recently in deep tech. And so helping Unitary Foundation, with partnerships with operations and everything like that.
Thank you.
Hi everyone, my name is Pierre. I work for IBM since too much time. And why too much time? Because I'm the oldest guy in the room, I think. Yes, I am. Then 19 years in IBM in 6 days. After working for CEA, doing some funny stuff, which is mathematicals and IT, and then mathématiques appliquées à l'informatique numérique. And I moved to IBM to do a lot of stuff in IBM. And if you have some time of your life to lose, I would be very happy to explain you why it is the best place to work in the world. But right now I'm in charge of strategic partnership for IBM Quantum since roughly 3 years, and delighted to be there.
I'm Maxence, so I'm currently a research scientist at IQ, a quantum software company. My background is in physics, condensed matter physics to be precise. I did my PhD in CEA, not far from there. And yeah, I joined IQ and quantum algorithm in general 2 years ago.
Hi everyone, my name is Adrian. So I'm working at Riverlane as a software engineer at the moment. Riverlane is a company that is building hardware decoders for quantum error correction and also building software for quantum error correction, which is my main focus at the moment because I am a software engineer by education. And yeah, that's pretty much it.
Hello everybody, so my name is Mamdou. I work at Alice & Bob. About my background, I have an old background where I had a PhD in quantum error correction from INRIA. But after that, I did many different things. I worked in the public sector in management and transformation roles, not related to science. I worked in strategy consulting at BCG, and I lastly joined 1 year ago Alice & Bob, where I'm in the business team, a bit like Jesus with a scientific background, but helping grow the business side of the company. And Alice & Bob is a hardware designer. We're working on building a fault-tolerant quantum hardware.
We have Leonardo online. We had
Yes, thank you. I think I'm the last one. My name is Leonardo. I'm the head of integrations at Entropica Labs. Entropica Labs is a company based in Singapore, and we are also active in the quantum error correction software side of things. Thanks.
Thank you all for the introduction. Now, what we have done is we've gathered some questions from our participants during registration, and I'll start with some of them. Then we'll have the audience ask questions if they have any. So I'll start with the beginning. like what skills should students start building now to prepare for a career in quantum, according to you? Anyone wants to speak?
It's a tough one.
I would say it depends a lot on where you want to work. If you want to work in hardware, such as in Alice and Bob or C12 or plenty of others company, IBM even, you need to have quantum physics, deep quantum physics knowledge. If you want to work on software, then you need to be able to write software. Ideally, you should be able to write software and understand what you are writing. So probably having a little bit of math behind it is a good idea. And having a little bit of understanding of quantum physics is also a good idea, but not necessary. I don't have any, and I can still work. So
Yeah, I think I agree. Like having a computer science background, even if you want to do quantum computation, right, is important because at the end of the day, you still write code in classical framework like this for most of the time, and you actually need a lot of classical pre and post processing steps anyway. So yeah, I think that's actually important on the software side.
In my opinion, there are two main tracks. You could go with the specialist one. It's usually people coming with a PhD, sometimes even postdoc. And there is also the other track, which is the one I know a bit more, say, trying to get a better picture of the ecosystem as a whole. So it's kind of a more, as we were discussing before, someone who is able to see what's going on at different levels. And then there's this rare case of people, I know just a few, who are able to do both. So they are very good at some specific problem, but they are also able to know about all the different actors in the ecosystem.
Thank you. Thank you all for the answer. Now, we had a few questions about the technology itself, and we've combined them. So let me ask, will quantum technology eventually be commonly used in everyday life, according to you? And what are the biggest challenges you think we are facing for making it a reality?
I will take the first part. Who in your background or life or whatever know that every day you are using COBOL? But it is the reality. I mean, every day in your life you are using COBOL codes and COBOL systems for transaction banking, reservation on stuff, etc., etc. But it's not visible. It's not like that. Then what do you mean by quantum being used in our real life? Will it be like COBOL, used every day by everyone, and something that changed the world from a B2B standpoint and then B2B2C standpoint? Or will it be like fast fashion stuff, LLM hype or whatever chatbot hype that will is just front office? I hope that quantum will change the back office of the company and not the front office of the company. That's my personal standpoint.
I can Pierre's perspective. Actually, quantum computing will be at least talking of what is proven to have a clear advantage, mathematically speaking, in the future at large scale problems. Will especially be useful to give a better ability to simulate physics. So it means, what does it mean in real life practice? Who is interested in this? People who are doing chemistry, people in pharma, people in material design, and also researchers who would like to advance knowledge about what is, say, superconductivity, how to better understand certain phenomena. And so, as Pierre is saying, it's more in the back office. And it's more in the longer term, meaning that quantum computing will enable the world to discover new things, understand better certain things, and then we will use them in everyday life. If you ask us, is the general relativity being to be used in our daily life? I would say not exactly that way, but the understanding of general relativity made us better compute how a GPS should work, and this is what we're using. So that's one step between what we are going to feel in our everyday life and what quantum computing going to bring. Yeah.
Imagine, I think sometimes, and it was also my case, sometimes we don't realize how many of the bottlenecks in industry are actually computational. We just take it, we don't think about it, but when we think about simulations, optimizations, there are so many different sectors like finance, etc., and their bottlenecks are really computational. So when you face the limits of classical computing, that's really what you should be looking at for detecting the impact on large society.
Thank you.
If I can add one thing, I may be slightly wrong. I will double check as we speak, but I think general relativity and special relativity especially matter for GPS. Actually, you need to account for both of them. Like you could work around it without using them, but it makes everything much, much simpler. And I think it's true for general relativity too. Be fun to double check. But for special relativity, I'm 100% sure. So you never know where this stuff is going to pop up.
Thank you. Thank you. That was. So now moving on, with this advancement in AI and ML, how do you incorporate this in your products, and how do you see this affecting quantum technology? Yeah, sure. So
AI.
Why? Aren't you happy with the question?
how do you incorporate AI and ML in your technology? Are there any problems that can arise due to that?
It's useful to design quantum computers, for sure. It's super important. When we're talking about error correction, it helps us better assess certain ideas. When talking about designing a design of a chip and how it's going to behave physically speaking, can help us also understand what we're seeing in terms of data, trying to pre-filter, give some preliminary ideas, etc. So this is the same way in which AI could help any industry. You have some processes where AI could help you because use some more cleverness. The other way around is quantum computing going to bring something to AI? It's a bit more speculative. It's not impossible, but it's a current area of research. There's a lot still to be proven and done. Maybe tomorrow when we'll have real quantum computers at scale, this will open avenues for research where we may discover things that we don't know about yet.
Anyone else want to? I can send something.
Yeah, maybe just a small impact for us since we do micro grants. So small projects for students that don't necessarily have access to a lot of resources. I think AI is actually something that can help us get more applications from people that don't necessarily have the resources themselves and can kind of leverage these big models to elaborate projects that we can then, finance and help. So actually probably a tailwind for us.
Yeah, sorry,
No, go.
I want to add in terms of like education and like this. It's always when you try to learn something new, and in particular like quantum computing, you have all these very specific packages you need to learn or to use to like create your circuits and then run them. In this case, like all the coding LLM and like this, just like speed up the what is this function, what does it do to I can actually build my circuit and run it. And so a bit like what you say for like this type of student project and education, I think there is some value here.
Let's be the devil's bad guy in the room. Maybe AI. And when I say AI, I mean, we need to say what is AI? Is it a symbolic one? Is it a non-symbolic one? Is it machine learning? Is it reinforcement learning? Is it rules-based model? Is it LLM, which is a small part of AI, which is just for the fancy stuff, etc. But maybe AI, with the progress of classical computing, will delay the moment quantum computer will be useful for some applications because they will make progress. And IDN, our customers, they don't care of using quantum of AI. They want a solution for their problem.
There's already a lot of example in physics where AI actually sort some like help understand like very complex systems. That
just wanted to share a really visual example of the connection between AI and quantum. So you have, as you were saying, you have quantum, for example, in machine learning, you have quantum machine learning, which is a particular way of using quantum computing for those kind of problems, which is maybe less mature. But I wanted to talk about the other one. So it's really classical machine learning for quantum computing development. And I can talk that at C12, for example, we have a dedicated team that is using machine learning techniques to improve the tuning of the qubits, for example, or they are optimizing the quantum dot formation. So it's always sorry, it's a two-sided coin, and it goes both ways.
So I'll switch gears a little bit, and here's a question: if you could teleport yourself 15 years into the future, what quantum technology would you hope to see successfully realized?
15 years?
If we have teleportation in 15 years, it means we can build much more connected quantum computers, right? Much bigger ones.
15 years, I will roughly be in retreat. Then I don't know if I want to answer this question. No, but that's let's say that we all have, and all the fields have very strong roadmap. Hopefully, in 15 years, quantum computing will be a reality. That means that we will have changed the world, and that's a common we. All the ecosystem will have changed the world if we succeed in quantum computing, and I think there is strong evidence that we will. Huge impact. Any?
From a more technical point of view, one of the things that I find personally exciting is distributed quantum computing. Even if I'm not talking about, I'm talking personally, not as someone from C12, because it really allows you to have different modalities connected on the same infrastructure. So we might be able to see photonic computers working alongside with cold atoms, etc. I think this is something that is being explored, and it might be a way to address the right part of the problems to the right GPU, and might provide better solutions. So it could be.
Okay.
So, I have a wild one, so maybe there's actually some interesting work done on using quantum computers to probe quantum gravity at like low energy type experiment. And this is, probably have no impact on direct life or like what is the nature of gravity at this scale. But I think it's a super cool idea to see that, as I say, we all work on a very practical point of view of quantum algorithm, quantum computing, or to make like value out of the market that exists. But you can actually use the same tools to probe like direct fundamental physics. And so if you can send the quantum computers to the moon, maybe we could, try to probe this type of thing. So
Elon Musk has to do so.
Now I would like the audience to get started with their questions if they have any. So please, if the audience they have any questions.
I can start with one. On the hardware side, when you're building hardware, as we mentioned before, a lot of this is quantum physics. How much of it is engineering? How much of it is engineering? How much are you working with engineers?
A lot.
I can say we are hiring a head of engineering now. So yeah, I think engineering comes as you know, it comes after the physics. So once you have some qubit that's already operational, you can start working about the integration to bigger systems, at least for the case of small startups. But I don't know if you have also another view.
I don't know if you are there in Paris in 2 weeks, but there is a stuff in EDF lab, which will be Quest IS, French national program conferences, and our head of systems and engineering will be there. And clearly, right now, I think we all agree that quantum research, physics, algorithm, etc., is fundamental and very important. But that we need to put a lot more effort in the quantum engineering and putting at scale if we want to move at scale and create a product. And that's what we try to do.
Integration, maybe.
Exactly, integration.
HPC, integration to HPC, this kind of.
That's engineers' work. But that maybe came back to your first question, is that if you need to, from a student's point of view, take one step from school, curiosity and capabilities to learn, because it's just the beginning of your very long journey. Look at the Mamdou profile, my profile. We have some history in the field. We have done many different jobs, works, whatever, and then that's what we call engineer in France, but that's what others say engineering.
And anything like control electronics, I don't know, anything related to integration is super important in quantum computing hardware providers for help.
Of course, you're all aware of the race of achieving quantum supremacy, quantum advantage, every other year some company comes out like, okay, we have achieved quantum supremacy, we have achieved quantum advantage, and then some other, no, you have faults in this. But lately, I've been hearing a lot about high performance quantum computing and how I think IBM has given some proof that apparently that is the ultimate way to achieve quantum advantage, and a lot of research has been going on, I think. So like, I want to know what's the perspective, like why are suddenly people are like, okay, high performance quantum computing is the most probable or plausible way to do this. Is there any reason behind it, and what's the technology, like what's the idea behind this? And
what do you call high performance quantum computing?
Quantum-centric supercomputing, or the hybridization made by Pascal and Pascal. Exactly. I think all the terms is, if we want to reach, there is, you know that by heart, that there is multiple, what we can say, regime in the quantum field. Let's say that they are the proven fault tolerance algorithm. They are and proven by pen and paper demonstration. And for that, obviously, we will need a fault tolerant quantum computer. Then no one is able to prove anything with that right now. And then there is what we can say, that how can I reach quantum advantage with the technology we have today and not the technology we will have tomorrow. And that's exactly what we work with our partners. And the good example is RIKEN. And RIKEN, we published a method, that's a public method, which is called SQD and SQKD, sample quantum diagonalization, sample quantum Krylov diagonalization, or sample Krylov diagonalization, I forget the name anyway. And that's, you use classical computer to prepare the quantum states, and you use classical computer to do the post-processing of the output of the quantum computer, because you know that the quantum computer himself will never give you the full solution to your problem, because at the end, the main question is, what is quantum advantage? And we strongly disagreed on the word supremacy when it was used by some members of the ecosystem, because it makes no sense to compare to something that makes no value. Quantum advantage is, I can do something that is valuable for the task that is needed. And clearly, will IBM be able, with this partner, to demonstrate quantum advantage in the next year? That's what we have said. We strongly believe in. Will someone be able to say 10 days after, with the new methods, that they have succeeded to beat IBM methods? We hope so. And we hope it will be a fight until the next, I don't know one, but until there is no fault-tolerant quantum computer, I think this race will be continue to be on. That's also why last week we published a framework standard with some members of the ecosystem, and I think you are part on the story. Unitary Foundation is part of the story, is to forget the claim and focus on the mathematics and the stuff, and let's say verify with an external point of view what is said by a claim. And that's a long journey. That's not on-off.
So if I might say, the European Commission is really interested in advancing the hybridization of quantum and HPC, and just as we were saying, quantum computing might be useful for certain computational workflows, but not all of them. So in this direction, there was the EuroHPC call launched by the European Commission to fund consortiums of startups and other companies who want to work in integration of HPC and quantum. So there's a clear political will, or to encourage this for different reasons.
The science behind the political win. I mean, companies are doing science.
A very quick comment also on that is that quantum computers, one of their goals is to try to solve problems we cannot solve already. And because they are very slow, like reasonably, we won't have like gigahertz clock frequency of a quantum computer, if that makes sense. And so in order to get advantage or to solve a problem faster with a quantum computer, we really need to have a very large problem so that the asymptotics of the algorithms starts to kick in and you're not in the pre-asymptotic regime. And so where are these problems currently solved? In HPC centers. So that's also an argument for like closely integrating. You have a last one, which is you will need HPC to drive a quantum computer. And so like the infrastructure in HPC center is already there. All the cooling, all the electricity. You need a lot of compute to drive a quantum computer. You need racks of classical hardware. You need to cool it. You need decoders. You can find and you can host that in an HPC center. You cannot host that in plenty of places that are not made for that. So it seems like a clear first step, at least.
I think like it's compatible, like in terms of.
I wouldn't say compatible, but it's less incompatible, and we need to make it compatible.
You can integrate it. Actually, current, I mean, that's actually a job. If, some people might be experts in integration to HPC centers or companies, and that's something very important at this time. Integration.
You spoke about combining several qubit technologies. Which advantages do you think it could have?
You mean like distributed quantum? I'm totally not an expert in this. I just
making part of the problem with transmon.
Yeah, exactly. Maybe someone here knows about distributed quantum better. It's just what I heard is that some problems, as you said, might be addressable better by. So the idea is to have quantum links between these different modalities. And this is not just theory. There are companies in France right now working in the projects, because this is always like proof of concept. So you try the technology in some kind of consortium, but it's not just theory. It's actually in terms of advantages. That's something I cannot answer.
Let's take a step back. We are not doing that for nothing. We are doing that to solve, as Adrien said, problems that is very hard to solve. And what we have seen right now in the industry, let's forget the quantum world, is that there is a good fit for purpose stuff. That's where open source came in the room, and capabilities to be agnostic to the different kind of technology behind that. That's what we see in the classical world. My customers, I worked 16 years in IBM, not for quantum, and they don't care about how it is solved on the technology basis. They want to have a solution to their business problem. And at the end, if the best solution to their business problem is to mix classical, multiple modalities of quantum, etc., let's do it. The main issue for them is they also don't want to see the complexity in the back. Then what is the kind of layer we need to invent from an algorithm standpoint, from a software standpoint, from an integration standpoint, to minimize the complexity of the beauty of the different technology in the back, and to make the interfaces with the problems for the customer. Right now, if you want to solve an optimization problem, I think that Cplex or GuruB are the best way to solve an optimization problem by far compared to a quantum computer. And that tomorrow, maybe it will be Cplex/GuruB. I'm not only talking about IBM. Cplex/GuruB /cold atoms /gate-based quantum computer, or any reinforcement learning stuff. The question at the end is, how do you manage the algorithm? I think we put, and that's a vendor company that is saying that, we put too much time in the hardware and not enough effort in the integration and the software stack and the business maturation on this stuff. And I mean, that's a personal standpoint on this.
question I will build on that, like how you can manage between the gap, like between the communications and like the gap between like your hardware. Can really manage that.
No one said that you need quantum communication to make quantum computers communicate. It's just that if you leave the quantum world to go to the classic world, to go to the quantum world, you take an additional exponential cost of computing at each layer of the stuff. That if it solves the problem and that there is a business value with this additional cost, why don't we do that? Integration, let's do with what we have. Let's integrate with classical network, quantum computer, and see how we can make a good use of that. And maybe in the future, we will do quantum communication as we said.
At least I already good results from IBM on this, because they use like two computers with like classical link between them, and like showed like very nice, like that it actually works, where you can actually make it work in real time. So.
Very good.
One additional thing to what has been said here is the day will reach the necessity and the ability to solve very big problems. So one single quantum processing unit is not going to be enough to solve it. So you would need some communication between different devices to have a global quantum computing capacity that is stronger than the individual ones. So it doesn't mean that necessarily you will have different modalities. It could be the same modality, the same quantum one, but you would need some quantum links between them. And it's an area of R&D, obviously, to be able to find the right communication wire with as minimum losses and interactions with the environment as possible. It's challenging, but it's going to be required.
I'm very sometimes afraid by the quantum ecosystem of the little knowledge they have of the classical ecosystem.
Actually, so that was my point I wanted to make. Like this already exists in the classical world, right? You have solutions that use CPU and or GPU at the same time, and now there are even like this AI made chip that starts to appear. And when as a user you use it, you don't know where it runs, right? But you get results from different modalities, classical modalities, but still the same. So
these took 60 years to build. So let's give us some time.
It's also a stuff that the quantum spaces. We don't have to reinvent every wheel. We have to invent some of the wheel, but we don't have to reinvent every wheel. There are a lot of stuff working in the classical spaces, and because of the silo of the research, the way, especially, I'm sorry for that, public research is very siloed. We don't need. I mean, look outside.
People don't know what is available and what is. Yes. I mean, this reminds me of a video I saw where it was basically a quantum scientist telling why she left quantum computing, because she was saying that there's not enough problems that we actually need quantum computing to solve for right now, because we have a lot of other technology right now, like machine learning and other high performance computing, other type of optimization algorithms and other stuff. Like we have to find true problems that we actually need quantum computing to solve for. That is the search that no one is doing. Like,
I actually don't think we need more problems. We need more algorithms to solve problems, which is a different questions. Like you could say a very classical problem, which is computational fluid dynamics, still bottlenecked by calculation. And you still have a lot of people working on quantum methods for that. They're like right now not very efficient, of course, but it's more about developing algorithms for specific problems and not relying on short algorithm to carry the quantum ecosystem forever, in a sense.
Sorry. Okay. Yeah, actually, since you mentioned the gap between the hardware and software, I have a follow-up question regarding software. And the question is, because we don't know how much at the moment you rely on the hardware development, and since there are so many different approaches to implement this, and what do you see the future of the development of software? I mean, if you can be done in a very abstract level, or it's
software you're talking about, because in the quantum startups you might have people working with the database of of the data coming from measurements, you may have also emulators like we do in C12. So I don't know exactly.
For example, like when you talk about like decoder, right? I would assume it's really specific based on the hardware and the code you choose. And I don't know, like in other like approaches, them I don't know if it's also transferable or more general.
Personal opinion, from classical computing and classical software, we learned that zero cost abstraction are not a thing, which means that when you do an abstraction, you pay a price. It might be very small, you pay a price. In quantum computing, for the foreseeable decade, probably we won't have big enough chips to be able to pay any price. We need to be able to be as close to the hardware as possible, because the chips will be too noisy, the chips will be too small for us to be able to waste resources of these chips, like very small resources, into abstractions. That's my personal opinion on where we should go, which is no abstraction at all. You need it somewhere. Eventually, you need some kind of abstraction, because else it's not doable. Because you cannot tell someone you need to know the whole stack up to the pulses of the hardware in order to compute, to like do your algorithm, which means you need a computer scientist with algorithm knowledge, as well as a hardware scientist with hardware knowledge. Good luck finding that. But we need the less abstractions possible. My opinion. Others might disagree.
One of the questions there is that you obviously, maybe one of the questions thinking about is that the near future quantum computers will be still too small to perform as many tasks as we would like them to do. So here, one of the issues is how can we squeeze them to the best? And so any overhead in terms of size of resources, would like to avoid it. So we'd like to have really focused, really optimized solutions for them. And for example, the error correction is one of these very interesting examples. So we need to have error correcting codes that are super adapted to the given hardware that is working to take the most out of it.
Let's take Qiskit. I'm sorry, that's the Qiskit. Let's assume that we will talk a little about this fantastic software that you can reuse and sell to anyone. Most of the part of Qiskit are agnostic to the hardware, but the transpilation, which is linked to the hardware execution, the part on that is specific to every vendor. And the way it is done by Alice and Bob, the way it is done by IBM, the way it is done by Rigetti, the way it is done by C12, etc., is dependent on the hardware for exactly the reason you mentioned, is that the abstraction layer is at the people that think about the problem. But when it comes to execution and create the ISA, the integrated architecture part, which is very dependent on the hardware, because we want to be as fast as possible, because we want to be losing the less performance as possible, then it comes to the hardware part. It doesn't mean that you lose the agnosticity, but it means that part of your code in Qiskit need to be optimized for each target architecture. And that's not the same. I mean, from an architectural standpoint on the software stack, there are stuff that are dependent on the hardware to have the best performance, but that doesn't mean that the overall stack is not agnostic and give you an abstraction layer. Then depending on who you are, if you are someone that wants to optimize the pulse, you will need to be aware of how the hardware is working. If you are just someone that wants to run the circuits and no one cares, and you run one day on IBM, the second day on Alice and Bob, the third day on C12, you don't care on that. You trust the vendor to give you the best transpilation software, because that's in our objective. Both of us and also provide the best solution at the end.
Also related to Qiskit, actually, at this time where we don't have the real computers yet built, this is what I personally and also C12 believes, that having a platform, software platform that is running on classical computers, but it has the noise model of the computer that you are building. I don't know if you guys have you heard the term before, emulator? I guess so. So that also, and this is not my background, but what I heard is that the state vector emulators, they don't incorporate the noise models of the platform you're trying to build. This is why C12 decided to build on Qiskit, the Qiskit platform. We decided to build our own emulator of the computing we are building. So what does this mean? It means that the algorithm developers, they can already start debugging, working, and algorithms that will be native to our platform, even if we don't have the computer yet. So this gives us extra time.
Very quickly, another parallel I can make is, to me, at the moment in quantum computing, we are at the stage of where we were in classical computing when launching something to the moon, for example, where you have very small processor and you cannot afford to just write a C program on it. You have to write everything in assembly or everything in the low level stuff so that you know exactly what happens and you know exactly that what you're doing is close to the optimum or close to the best you can do.
Maybe just oh, sorry, go on. No.
Yeah, just from a wider perspective, I think kind of one of the premises of Unitary Foundation is the important, open source in software development, because there is a little bit of a gap between the focus on hardware and the kind of software lagging. So whilst, as we're saying towards the end, it's going to be very important for each hardware provider to have specific software. For now, there's a lot of collaboration that's needed, a lot of company-specific software elements that are going to be very important to create collaboratively, and that's why kind of Unitary Foundation is here to bridge that gap and help us make sure that software will be ready when the hardware is ready, because that's where the big bucks are going to be.
Thank you. That was my counterpoint, which is I agree with what was said, and if you want some optimized implementation, you need to fix some hardware condition, but also the only advantage proofs that we have were done without any quantum computers, right? In the 80s, 90s. So you can still have let's say fundamental algorithm research without fixing any of the hardware constraint. Will this be near-term applicable? Probably not. I mean, you don't know, but it's still possible, right? Even without thinking about the machine.
But let's think again about the software stacks and the stack of the software stacks. Quantum error correction. 100% agree with what Mamdou and Adrien say. It's hardly linked to your hardware. You need to have a deep understanding on how to build your computer to build the best quantum error correction stack on top of that. Algorithm. Do I need to care about the hardware if I'm working on the theory standpoint on the algorithm side to change the way, I don't know, CA or Safran or Airbus will express their problem, which is a partial differential equation problem, into Boltzmann equations? How do I solve the Boltzmann equation with a quantum computer? What is the best method to do it? And can we move away from QAway, VQE, and something else? Yeah, exactly. And that's the full world is stuck with few algorithms and not enough people spend time on, hey, can I have a brilliant idea to do something differently and to express my simulation problem, my business problem in a different way that will take advantage of the quantum mechanism? That's a huge part of the software that no one is talking about. And sometimes it's not, this one should maybe not be agnostic and open source. It's very IP driven. Then if you are, I mean, some companies make their money during a long time on this very specific tiny business model. How can I do, I don't know, Dassault System, for example, or ANSYS? They made all their money to simulate very good stuff. And then there is all this funny middleware integration, AI for quantum. How can I use the LLM to help my creation of deep knowledge circuit And I will go inside the details of but for the full circuit, I will first create a long line of, and all of that needs to be done with the most interoperability capabilities, the most agnosticity to the hardware, and capabilities to be reused and resell. That's our behavior, and that's why we think Qiskit is key.
Since it's also kind of about career, I have a two-part question. Aside from this place here, what's a good place for students to go to meet these companies, and what are interesting, especially online resources where they can learn parts of quantum computing that they want to familiarize with?
I think I can give one answer. Probably not the only one. Hackathons are actually so it's actually also come from the classical computer science ecosystem where you can actually get your hand on real problems. So hackathons that are well organized actually have companies that come with some use case, like some problems they define for the hackathon, and then they also put you in contact with a technical side, like some startup or like companies working on computing, and so you really can make this junction between what are the problems, you have someone to help you build a solution, and then you actually get your hands on on the topic of building circuits, algorithms, and things like this. And this can happen actually online. I think there are a few platforms that do it, and also like in person in Paris. I think there are like a few of them every year. So if you can, register. I have no affiliation. I don't know if you're like if you need to pay to register or not. But I think that's a good way of actually getting a view of like the full, as I say, like full stack, right? You to design the algorithm. Usually you even have some compute time which are like provided, and then you have an applied problem, and you need to bridge all of this. So.
In France specifically, you can also have a look at what Le Lab Quantique is doing. They are organizing monthly or every 2 months, depends. I think the goal is to make it monthly. Meetings with companies. Often it's like one person from one French company presenting their work, and then it's a time for exchange.
I was going to mention Lab Quantique since I also work there, so so go there. And then we also have a Discord channel in Unitary Foundation, which has like careers, which has we host events. Like for instance, every Wednesday we'll have Quantum Wednesday, where somebody comes and presents a piece of tech that is interesting or a paper. And then I will also say that like beyond the classical like YouTube and Coursera and whatever, the ecosystem is still surprisingly small enough that you can reach out to a lot of people, and people are super friendly. I was surprised when I came from like investment banking and moved to quantum, and I was just like reaching out to everybody, and literally I would say 99% of people just come back to you and introduce you to people and will answer your questions very happily. So really don't feel afraid to reach out. But yeah, other than that, I would say Discord and Lab Quantique.
GitHub. If you are in the software stack, just apply and work with the community, contribute to the community, exchange with your peers from the community. And that's once again the beauty of the open source world that we have in front of us from the software stack point of view. That most of the classical and quantum software right now are based on open source. A strong way to be connected with the community is to contribute to the community and make friends online, and then you make them in real life, and then you get a job. That's the reality.
There's a job channel.
That's in reality what happens.
Actually, I would really say so that it's important to show that you're active. That it's not. I think today is not. It's not enough to say, "Hey, I have a master's in quantum, whatever." I'm saying it's very important, and actually, no. Actually, this was what I was doing.
You're totally right.
It's like, no, I'm an engineer. I studied here. I did research, and people are okay. But what can you provide? And this is where I really want to agree with you, Maxence, that going to events where you can already do something. It might be a hackathon, might be GitHub. Just that you can prove, and it's not just CV that is talking for you. It's you there. Also, the CV helps, but it's really like I'm doing stuff now for you, and you are seeing that I'm doing it. And this is exactly what you said, is said in a different way. But
yeah, I mean, we just hired also a quantum software engineer, and I looked at GitHub every time I had the chance, because you can actually see what people have done, right?
It's general career advice, but
Yeah.
it's really like nowadays, I think the market is really saturated. It's very hard for people to get jobs, especially in this field. So I think what makes really the difference is to go out there, talk to the people, and do stuff. Where it might be wherever, it might be coding, might be writing articles somewhere like LinkedIn or whatever. Just do something that makes you different to the others. That would be my personal advice.
Yeah, actually, but this is also, so as I said, we just finished something, and we had very strong candidates with very strong like theoretical background. They have quantum information. They have like a lot of very strong fundamental, I'd say on their CV from their master or PhD, like this. But then when you ask them, what did you actually do? What type of tools did you implement? What did you use? And they're like, I played around with Qiskit, and you're like, yeah, but we do like 90% of our day job with Qiskit, so you need to be.
Like, how can you help the company? That's the question.
Yeah, exactly.
Even
if you want to do research, I would like encourage to have like some hands-on experience, because pen and paper it still exists, but it's hard in companies, right? It's
So we have time for one more question.
Yes, I have one question. So imagine you are today like 20-year-old guy. So what do you want to do to start your career?
I would love to. I would love to, you know. What is the advice I will?
Yeah, what do you want to do tomorrow to prepare for the career for quantum if you are very old?
Be sure you want to be in that field, and be sure that you are interested in that field first, because like being in quantum is not a goal. Being happy is a goal, and so try to be happy in quantum. So first, be sure you want to work in that. Be sure you are interested in that. If you are, then interest yourself. Like try to go and read papers, try to talk with people, try to make links with people, let people know about you. A lot about having a network, which is terrible to do, but sadly the truth. And a lot about showing what you can do. So maybe like do collaborative research with other people if you can, if you are in a field where you can do that. Try to collaborate on open source projects if you can do that. Follow your interest.
I would say also just be interested in the whole ecosystem, because sometimes what's the problem is that when people are very experts in something, they are the best. They can show you the slides on error correction, and they are able to tell you all the different relevant challenges in their field, but then they have no idea whatsoever about what people in the same field are doing. And this ecosystem view is very hard to gain. I would say again, Le Lab Quantique is a really good resource, because they are trying to federate the different layers in the field. So just be curious about the ecosystem while staying an expert in your topic, I would say.
Maybe I would just add last one point that that goes in the same sense that what has been said is there are so many information about quantum that is going every day, make it super hard to follow if you don't have humans, if you don't have people to talk with and to hear from. When I joined Alice and Bob after spending years away from quantum computing, I didn't have that internal decoder that helps me assess all this information I could get every day and see this is relevant, this is not. What are the what can I take out of this information? Is this one useful or not, etc. And it's by talking with people inside the company that I could have this way of interpreting things and understanding things. So all these advices also help you like get in touch with people to build your capacity of understanding what's happening in quantum computing.
I have like last questions. What's the last message that you can say to the audience about your company, like in one word?
So what?
Can you say like in one message that the audience can remember from your company?
The advice from our company, you mean?
Yeah, I mean one message that can remember.
I can start if you want.
Yeah.
If you think quantum error correction is the only way to go, and I think so, come and join Riverlane.
I could use the same for the exact same message.
But I said it first.
If you think fault-tolerant quantum computing is the way to go,
then I think it's slightly different because we actually talked a lot about integration, and that's a nice topic. And I could actually work a lot on this middleware layer, and so this is actually very interesting and like surprisingly difficult thing to do at some time. So slightly different take on why you should join us, but.
My phrase is we are using carbon nanotubes as a road to fault-tolerant quantum computing. So if you are interested in the material science part.
I guess I'm the hippie of the group, but we're open source, so contribute, come help. We're very open. We have a lot of channel. And if I can just answer the last question on the 20-year-old thing, which is very cliche, but very true, especially for me when I was 20, which is don't self-discriminate. Like when you're looking for career options, when you're kind of curious, you don't feel like you have the right skills, etc. Just go for it. It doesn't matter. Like it will absolutely work out. If I did it, you get 100%.
And confidence will come by doing things. Don't be afraid. Like I don't have the skills to do it. I think we've all experienced that.
Yeah. Imposter syndrome.
That you are 23, 24, 25 when you get out on your that's the beginning of your working life. You are still 40 years ahead of work in front of you. You know, no, but that's the reality. You get out of the school at 25, still the beginning of a long 40 years journey. Then if you think that that maybe will happen for some of you, but if we think that the ecosystem that you work when you will be 25 will be the same when you will stop working when you will be 65 or 67 or 70, just forget it. Look at the world in the last 15 years. And then it comes to why IBM. We are there since 114 years in the tech company. We have seen the cloud. We, because of our systems, launched stuff on the moon. That was us, you know, that, yeah, sorry for that. That was us. Every day on business, you are using an IBM system on an IBM software stack. Let's say that we are not that bad in quantum computer. We have done stuff that did not work. We have failed in some spaces, but we are still there. And yeah, you know.
Well, I personally prefer to join a startup, but that's, I guess, it's also a matter of
that's typically the startup way to think.
If you like
the best,
you know, if you like, is don't mind the risk. Don't mind the risk.
I'm the best. Come on, guys, don't say that. The ecosystem is bright. Everyone is brilliant. You will maybe succeed, but they are company. That's why you
specialized in something. Go to a startup.
Yes, exactly. That's what. If someone asks me, is Google a bad company because you are IBM? Obviously, I am not stupid enough to say that Google is a bad company. That's the same for Nvidia. That's the same for Microsoft. That's the same for this kind of company. At the end, choose the company that respects your value. That's important. And that's another point where IBM is the best place to work. That's a personal standpoint.
Yeah,
and Leonardo online, yes.
Yeah, it was a bit difficult to join from online, so I was enjoying hearing you guys. I'll just echo, I mean, most of what you guys have said. Maybe the only thing I will add is always value learning how to work in a team. That's a problem that I see often with new hires we have at Entropica. People come out of academia and they're like lone wolves. It's hard to do all of this alone. So it's all of the soft skills are also super, super important. I think many of the other panelists have said this in different ways, but don't underestimate that part. You can be a top scientist, but it may be very difficult when you start working in a company. And whether it's a small startup or IBM, you'll need to work with other people, and there's a lot of soft skills that become very, very important in the quantum sector too.
Meilleur conclusion que ça. C'était émouvant en fait. J'ai une petite émotion moi quand je l'ai.
I almost cried, Leonardo.
That was my objective. I will put that in my CV.
Leo, are you staying?
There is
Leo,
of my mail.
are you staying?
Okay.
Please, everybody, please stay.
Et je peux pas me connecter sur ça.
Yeah. There's like a particular one we do.
Everybody come in, please.
Just one picture, sorry.
Et ça marche avec le VPN. Le VPN aussi.
We want to take a picture of the event.
Oh, rentrer dans le RFNA.
Leo?
I don't know how much you we have, mais c'est sûr. Ouais, avec ça, je suis non. When I was in high school. And I was when I really
Take a picture for the whole event.
Oh, Lincoln in Sheffield.
Sheffield, I know, but I've never been.
I went to Sheffield. Sorry. Where?
Everybody can take a quick picture.
Yeah.
Where do we go?
I think this, and I will show the video of Leo. Then please and all the participants.
Là, depuis ce matin, ça devait amuser, ouais. T'avais d'autres interventions? J'en ai une là.
A picture of everyone?
Peut-être
I like France because it's similar now. Okay.
après,
South of France, kind of similar.
c'est quoi le choix?
Ah, ouais. Also have
Yes.
I don't think we need your photo. You can remove this one.
Try to remove the...
It would be a beautiful
picture
in a picture in a picture.
Like
an eternal.
Everybody say haha.
Haha.
Haha. Qiskit.
We'll reuse that one.
You want to join?
You want to join?
Yeah.
Another one.
Another one, sorry.
Ça marche, cuisine. Donc la liste, ça marche.
Qiskit.
Qiskit.
Ali, ça ne va.
C'est tellement propagande familiale.
Yeah, so basically it's like three main things, which is big micrograms. That's like $4,000 grant. And then second is research, so that's where you have like error correction, and then project things.
Yeah, so I'm like,
I think you're asking wrong. Because I can't get into the but I know that and it's so recent, but I can absolutely.
Not a lot.
Donc, je peux me donner les slides. Ah, tu m'as envoyé, voilà, c'est bon.
So like I joined a month ago, so I like forget people's names and stuff. Yeah. When you get your email,
I just want to make sure. Yeah, I'm saying. Yeah, you want to see. So Riverlane is not able to. I don't have the. Also, guys, with collaboration with. And that remember
And that will also send you the metric stuff.
Yeah.
Yeah, and then like the last thing is more like about hackathons and what else mentioned. Like community driven.
That they can't. Eventually, they find out that they want to do a PhD, and they leave for 3 years, 4 years.
Yeah, I'll put you in contact with that.
Oh, you already did. That easy to do their PhD as part-time. So,
No, we were doing.
ask me an email. Send me an email. I will
I got it right.
We are discussing this whole part between the circuit and the hardware, right? Like, you said that you need to get a thing that is optimized.
Yeah.
Yeah, hardware, but we're using just like all the optimization steps that you need for the circuit, you know, small enough that you can run. Improve the results that you cannot do magic. Also, it's actually a US-based company.
For applications.
Because they're the only one. We don't have an office right now. It's mostly because I'm the only one. No, like reason to.
Best in your life. The best in your life.
But yeah, otherwise it's like US or Ukrainian.
Yeah, I feel like you're committing.
I have like always sprint out. Like,
very nice. I'd like to
see that I like. I'm like
so. Because I'm just scientist, so it's actually reading a lot of papers, but that's the
I also forgot.
and then it's also
I agree.
Like do this mapping. You can find the map and use a lot of
when I was younger, when we like really got out of like what I think I know, but
and then come up with some like ideas of actually like
For software engineers, just software engineers.
like some new way like optimization like this.
That's what you will
Approach from doing like all this type of
Guys,
targeted, let's say, solutions.
I fully agree.
Yes.
It will open up a lot of doors.
That's what's going
Exactly, that is why.
We will have the IBM.
You have my mail.
Did you send it in the Discord?
Yeah, this woman.
Oh, and in Discord.
And Discord? Yeah, I think.
I'll send you the my calendar.
Merci. On fait des questions au début, c'est on les connectait par des gens qui.
C'est dans le communauté française, c'est bon par la
I'm not. I have to head back to work.
Well, it was nice to look up. That was great doing a very business. The next.
Thank you for having me.
Non, c'est bon.
It's all you, right?
Thank you for coming.
My pleasure. And enjoy the rest of the.
Ah oui. Quand la campagne de recrutement finissait dimanche dernier.
Oui,
Ouais, je pose mon avis. C'est important, toi. Ouais, moi je vois aussi. Je suis preneur.
secret, tu es là. Oh bah oui, lui, il a l'air vraiment.
Oui, je suis française.
Un nouveau sujet.
On est d'accord.
Ouais, j'ai regardé
Riverlines. Ça vous
Je crois que non. Je crois que non. En fait, il y avait beaucoup.
Cette revue, c'est sur le titre de saison, il est passé sur ça. Et apparemment, c'est pas cool.
À vérifier, mais je crois que non. Bah, le mieux, de toute façon, c'est d'être en présentiel. Je vérifie dessus.
Il n'y a aucune urgence. Moi, ça m'intéresse d'avoir les résultats. Ouais, c'est un peu, ouais.
Sur les offres de stage, normalement, c'est parfait.
Plaisir. À bientôt.
Should we begin? In French, in English d'ailleurs, je ne sais pas ce que je fais.
Ouais, peut-être, les gens en ligne.
En ligne aussi.
Then in English. That's fantastic.
You can talk actually.
English is forbidden. No worries. No worries. How many people do we have online? 4 people. Then, how many times I have? 40 minutes, 15 minutes, 1 hour? How many? 1 hour. 1 hour. Okay. Questions. And first, ask question when you want. That's the objective. No, but that's really the objective. Not there to do. Important. I put ENCO, not only Université Paris-Saclay, I know that. Thanks for organizing this event. That's made a lot of importance for us. We strongly believe in the ecosystem. I will not spend too much time on the marketing chart, etc. But obviously, yes, I will talk a little about IBM. That's why I'm there today, to talk a little about us. Feel free to ask questions whenever you want. And our objective this afternoon is to go through the innovation which are inside our quantum roadmap. And some parts will be detailed, some parts will not be detailed. To be honest. Yeah, then IBM Quantum is part of IBM Research. You maybe have seen that IBM Jay Gambetta, our VP for Quantum, moved to IBM Research head of research position, and that's good news for us. That our boss is moving from quantum to research. That's the importance of quantum inside IBM. Just to give you that, we have many locations in a lot of places, and we were discussing that during the lunch. That if you think you can bring something to IBM, don't be trapped by the location. Just apply, and if your profile makes sense, we will manage to open a post and a position where you want to stay, in accordance with our locations in the world. We are all around the world, and I think one point that wasn't discussed this morning is that we clearly believe, and that strongly believe, in the convergence of bit, qubits, and neurons, classical, quantum, and AI. Let's say that way. And we don't think there is one solution that could solve them all. I'll reuse it. The objective is really to do the convergence of that by multiple software stacks, by open source stuff, by capabilities, and by algorithm standpoint. Last, we have 2 missions in IBM Quantum. I will not talk about the second one. If you are interested in, you can ask me the question. But there is a wonderful IBM web pages. Our main objective is bring useful quantum computing to the world. Not that the second one is not important, but that's much more easy, and that's not a quantum problem. That's a classical problem. How will I implement quantum safe algorithm at scale? And if we divide the practical path to useful quantum computing into 2, I think we can separate in 2 different stuff. Is run quantum circuits accurately on quantum hardware, software embedded, but at the end it's an hardware task, or at least a hardware vendor task. And on the other